this lecture, we're going to continue looking at examples of related rates problems. So for our first example, we're interested in finding at what rate is soda being sucked out of a cylindrical glass that is 6 inches tall and has a radius of 2 inches. The depth of the soda decreases at a constant rate of 0.25 inches per second. So we know that in these problems we often want to start by drawing a picture of what we're looking at. So we've got a cylindrical glass. The glass, we're told, is 6 inches tall, and its radius is 2 inches. So we're given information about the rate at which the depth of the soda is decreasing. So we want to imagine that inside of this cylindrical glass we have some amount of liquid whose height at any particular time we can call h. So then we're given that dH dt, the depth of the soda, is decreasing at this constant rate. So we know that the rate of change of the height with respect to time is negative 0.25 inches per second, okay, because that depth is decreasing. So what is it that we're trying to find? Well, we want the rate that the soda is being sucked out of the cylindrical glass. So that's looking at the quantity of soda that's leaving. We can think about that there's, you know, a straw in here and we're drinking the soda. We're interested in finding then this amount that's being sucked out of the glass as dV dt. Okay, we're looking at the volume of soda that's leaving the glass, the rate at which that volume is changing with respect to time. Okay, so we don't know what that is. So since we're looking at volume and we have this height information, we need to use our volume of a cylinder. So the volume of a cylindrical quantity here, and this is representing the volume of the soda itself, is pi r squared h. Okay, so initially it looks like we've got 3 variables here. I'm really only interested in what's happening with v and h. But if we think about our, let's see, our liquid, our soda in this glass, and think about its radius, we realize that at any particular height, even when the height is going to be very small of the soda, even when it's almost empty, our radius is still the same as the radius of the glass. So the radius is constant. So r is not changing as a function of time. The radius of the surface of our liquid soda is equal to 2. So before we take the derivative, we can plug in anything that is constant, anything that doesn't depend on t. So we have v is equal to pi times 2 squared h, so we've got 4 pi h. And now I have an equation that relates the two variables that I'm interested in, and next I want to take the derivative of both sides using implicit differentiation in order to find what dV dt is in terms of dH dt. So if we take d dt of both sides, we've got dV dt equals 4 pi dH dt. Okay, so this relates our two rates. So now we have that dV dt is equal to 4 pi times negative 0.25 or negative 1/4. So we end up with negative pi, and this is units of volume, so this is negative pi cubic inches per second. So in terms of the way the question was phrased, we're being asked at what rate is the soda being sucked out of the glass. So it's being sucked out at a rate of pi cubic inches per second. Okay. Since the being sucked out takes the place of the negative sign in our computation there. So it's just important to remember that when you're dealing with a cylinder, you've got this constant radius information. Okay, so let's look at another example. So in this situation, we've got a baseball problem. We're told that a baseball diamond is a square with side 90 feet, and a batter hits the ball and runs to first base with a speed of 24 feet per second. At what rate is his distance from second base decreasing when he is halfway to first base? So we want to draw a picture modeling this situation. So I've got my baseball diamond here. This is home. I've got first, second, and third. Okay. I know that each one of these sides is 90 feet long. So I can label that information on my diagram. Let's see, I've got my player that's running towards first place. So he's somewhere here. Okay, and we've got this speed of 24 feet per second. So I need to introduce a variable here that maybe represents my distance from first base. So let A be the distance player is from first base, so that as he's running towards first base, that distance is decreasing. So our dA dt is equal to negative 24 feet per second. Okay. I'm interested in finding the rate at which his distance from second base is decreasing when the player is halfway to first base. Okay. So I'm interested in finding something about the rate of change of that distance. So I need to call that distance some variable c. So we'll have c be the distance player is from second base. Okay, and we're interested in finding dc dt when the player's distance from first base is exactly half of 90. So when A is 45 feet. Okay, so we know that A is changing as time changes and C is changing as time changes, so we can't plug in any of those values to start with. But when we look at our diagram, we want to see how we can get an equation that relates A and C and this third side here of 90. Well, if I'm dealing with a square, then I've got a triangle here, a right triangle, and I can use the Pythagorean theorem to try to get a relationship between my different variables. So I can say that A squared plus 90 squared, okay, because this distance here, we're not interested in anything about the distance between second and first changing, that's constant. A squared plus 90 squared is equal to C squared. Now I don't want to plug anything in yet because A and C both depend on time. So in order to get my related rates, my related rate equation, I need to now take the derivative of both sides with respect to t. So I'm going to have 2a dA dt plus, well, the derivative of 90 squared will be 0, equals 2c dc dt. Okay, so now I can go ahead and plug in my information to try to solve for dc dt. So I know what dA dt is, that's my negative 24. I'm interested in what's happening with dc dt when A is 45. So I know what this is, I know what this is. I'm trying to find this one, okay, but that leaves me one unknown of C. So I have to additionally figure out what C is at the moment when A is 45. So I want to look at my triangle in that particular situation. So when A is 45, and this side here we know would be fixed at 90, we need to figure out what C would be in that case. So we've got C then would be the square root of 45 squared plus 90 squared, just using our Pythagorean theorem. Okay, so when A is 45, C would be the square root of 45 squared plus 90 squared. So we can see that plugging these things in, we now get 2 times A of 45 times dA dt of negative 24 equals 2 times the square root of 45 squared plus 90 squared times dc dt. So to solve for dc dt, we just have to divide both sides by this 2 times the square root. So we get that our dc dt ends up being 2 times 45 times negative 24 all over 2 times the square root, which comes out to about negative 10.733 feet per second. Okay, so we can say that the rate at which his distance is decreasing is at a rate of about 10.733 feet per second. Okay. So it's decreasing at this rate. Okay. Or we could say that the rate at which the distance is changing is this negative 10.77 feet per second. And if you didn't have a calculator, we could have just canceled these 2's, maybe done the arithmetic for the numerator here, but we would have mostly just left that in terms of the square root. Okay, but since we have a calculator, we can go ahead and sort of figure out about what that rate is going to be. Okay. Okay. Remember, you always want to have units on your answers, and you always want to answer the question in the context in which it was asked. Since we're being asked at what rate is the distance from second base decreasing, we can say it's decreasing at this positive rate. Okay, so let's look at a couple more examples with a few other variations on the methods that we might need. So in this problem, we've got two sides of a triangle are given to us as 4 meters and 5 meters in length, and the angle between them is increasing at a rate of 0.06 radians per second. And we're interested in finding the rate at which the area of the triangle is increasing when the angle between the sides of fixed length is pi thirds. Okay, so this 4 and 5 meters is something that's going to stay the same. So I've got a triangle here with 4 and 5 meters. So I have maybe 4 meters here, 5 meters here, and I have this angle between them that's increasing, so it's becoming a wider angle. So I'm given that d theta dt is equal to a positive, because it's increasing, 0.06 radians per second. And we're interested in finding dA dt when theta is equal to pi thirds. Okay, so we need to get some information to relate some of our different variables here. So what do we know? Well, we know that the area of a triangle is equal to 1/2 base times height. Okay, I can treat my base here as 5, and then my height is going to be some variable h. But I'm interested in somehow involving or relating my rates of theta and a, so I need to convert this into an equation that instead of having a, b, and h, has maybe a, b, and theta. Okay, since I know that this base here is going to be fixed, I can actually go ahead and replace that. I've got 5/2 h. I really need h to be in terms of theta. So if we look at this triangle here, we can think about what kind of trig function we could use to relate 4 here that we know and h. So if we look at sine of theta, for example, we see that sine of theta is equal to opposite over hypotenuse. So we have that h is equal to 4 sine theta. So now we can use this in for our h and write down an equation that relates a and theta. So we have a is equal to 5/2 times 4 sine theta, or a is equal to 10 sine theta. Okay, so now we can do our derivative. So we have dA dt is equal to 10 times cosine theta times d theta dt. Okay, so now I can plug in my different values and compute the rate at which the area is increasing when that angle is equal to exactly pi thirds. So we have dA dt is equal to 10 cosine of pi thirds times 0.06. Okay, the rate at which our angle is changing. So now I need to remember the exact values of my trig functions. So I remember that cosine of pi thirds is 1/2. So I have 10 times 1/2 times 0.06. So I'm going to have 5 times 0.06. So I end up with 0.3 meters squared per second. So the rate at which the area of the triangle is increasing is 0.3 meters squared per second. Remember, it's area, so we've got this square meters, and then it's our rate, so it's per unit of time. Okay, so sometimes we have to involve a couple of different equations in order to relate the variables that we're interested in. Now we want to look at one more helpful rule for computing certain kinds of related rate problems. So we've seen how trig or the Pythagorean theorem can come in useful in different kinds of problems. There's also a situation where we might not be dealing with a right triangle and we need to somehow relate our different sides maybe to an angle in our triangle. And this is where law of cosines can help us out. So what the law of cosines says is if I have a triangle that looks something like this, and I label my signs with the lowercase letters A, B, and C, and my angles with uppercase letters A, B, and C, where the uppercase angle is opposite the side with the lowercase label, then we have the following relationship. We have that C squared is equal to A squared plus B squared minus 2AB cosine of angle theta. Okay. It's also true that if we choose a different side here that we want to be interested in here, it's also true that B squared here would be equal to A squared plus C squared minus 2AC cosine B, and that A squared would be equal to B squared plus C squared minus 2BC cosine A. Okay. So what you want to note here is this is a generalization of our Pythagorean theorem, because if C is equal to pi over 2, sort of taking this first situation, so this is, capital C, so the angle is pi over 2, then we know that cosine of pi over 2 is equal to 0. So then we have that C squared is equal to A squared plus B squared. Okay, so this is the case where excuse me, if we have a right triangle, then our angle opposite this side would be 90 degrees, and this side would be our hypotenuse. So we'd reduce to our Pythagorean theorem. Okay, but this law of cosines is telling us what the situation is when we have a non-right triangle. Okay, so keep this in mind for our next example. So in this example, we have a plane that's flying with constant speed of 300 kilometers per hour, and it passes over a ground radar station at an altitude of 1 kilometer and climbs at an angle of 30 degrees. And we're interested in finding at what rate is the distance from the plane to the radar station increasing a minute later. Okay, so one thing we're going to have to be careful of is that we have our speed given to us in kilometers per hour, and we're interested in something that's happening 1 minute later. So we're probably going to need to convert that to 1/60th of an hour. Okay, so we also want to get an idea of what's going on in terms of a picture. So I have my plane being 1 kilometer above my radar station, and I have it climbing at this angle of 30 degrees. So that angle is going to be the constant rate at which the plane is climbing. Okay, and I'm interested in knowing at what rate is the distance from the plane to the radar station increasing. So I'm interested in finding something about this distance here. So I'm going to label that C. We'll label this side A and this side B here. Okay, so A equals 1 is constant. That's where the height at which our plane started, or when it was above the radar station, it was at that height of 1 kilometer. So let's see, in terms of the variables that we have, what information do we know? So we know our plane was flying at this constant speed, so that's the rate at which this distance B from where we started is changing. So we know that dv dt is equal to 300 kilometers per hour. Okay, let's see, since this angle down here is 90, we actually have that this total angle here is 120 degrees. That's going to be important in a minute. We're interested in finding dc dt, okay, when t is equal to 1/60th of an hour. Okay, so we want to think about how we can relate these different quantities. Well, this is a case where we have a non-right triangle. Okay, so we can make use of that law of cosine. So we can say that c squared is equal to a squared plus b squared minus 2ab cosine theta, and then we can put in some of the information that doesn't change as a function of time. So we know that c squared does change, so we have to leave that in terms of c at the moment. A is fixed, so we can put in 1 squared here. B squared changes. A is 1, so we have 2b. And our angle here is going to stay the same. So we've got cosine of 120 degrees. Okay. So we've got c squared is 1 plus b squared minus 2b. Cosine of 120 degrees is the same thing as cosine of 2 pi thirds. That's 60 times 2, or pi thirds times 2. So we're looking at cosine of that being -1/2. So we have c squared is 1 plus b squared plus b is what that part simplifies to. Okay, so now we can look at introducing rates because we're interested in relating these rates of dBt and dc dt. So I can say that 2c dc dt is equal to 2b dB dt plus dB dt. Okay. And now I'm going to be interested in using this information that I have to try to solve for dc dt. So let's see, I'm going to have to fill in both this c and this b value. So I need to know what those distances are when t is equal to 1/60th of an hour. So we know that the plane here is traveling at 60 kilometers per hour. So b after 1/60th of an hour, okay, that distance has to be the rate times the time. So it has to be 60 kilometers per hour times 1/60th of an hour. So we're looking at 5 kilometers being our value for b. So when t is equal to 1/60th of an hour, b is equal to 5 kilometers. Okay, well, what about c? Well, if I know what b is at a certain fixed time, I can then use my law of cosines to figure out what c is at that time. So I have that c squared is equal to 1 plus b squared of 25 minus 2 times 5 times my negative 1/2. So c squared is going to be equal to, let's see, we have 1 plus 25 minus this is going to be plus a positive. So we're going to have 5 plus 25 plus 1. So we have 31. So c is the square root of 31 kilometers. Okay, so we can plug in some of these values now. So we have 2 times the square root of 31 dc dt is equal to 2 times 5 times 300 plus 300. So we're looking at dc dt being, let's see, this is going to be 600 times 5, 3,000 plus 300. So we're going to have 3,300 all over 2 square roots of 31. So we can simplify that a little bit. So we can have 1650 over the square root of 31 kilometers per hour is the rate at which our distance from the plane to the radar station is increasing a minute later. Let me just clean this up. It's a little bit hard to read. So we have 1650 over the square root of 31 kilometers per hour is our final answer. Okay. The best way to get good at working related rates problems is to work lots of different examples. So you see many different situations and different kinds of equations that you have to use. Please let me know if you have any questions.